Assalamu alaikum. We are Team 4 and today we are excited to present our project Retro Style Tic-Tac-Toe Gaming Device using the AT89C51 microcontroller. So, what was our goal? We wanted to build a low-cost portable gaming device that can run on very limited hardware but still feel smooth and interactive, just like a real handheld game. Our system includes some key features. You can play player versus player with a friend or switch to a player versus AI mode where the microcontroller becomes your opponent. We use a 16 cross 2 LCD display to display the game and a 3 cross 4 keypad for user input. Now, the interesting part is we built all of this under strict constraints. Only 4 kilobytes of ROM, limited input output pins, and we have to keep it in low power and low cost. To achieve this, we use the AT89C51 microcontroller as the brain of the system, a matrix keypad for input and a LCD display for the output. Now let's quickly see how it works. When the user presses a key on the keypad, the input is sent to the microcontroller. The controller processes the move, updates the game logic, and immediately reflects the change into the LCD screen. In AI mode, the system doesn't wait. It actually calculates its own move and plays against the user, making the game more interactive. So when, even with the limited resources, we were able to create a complete and functional gaming system. This project shows how we can combine embedded system design with efficient programming to build something simple, fun, and effective. Now, I'll hand over to my teammate who will explain the system architecture in more detail. Thank you.
Now I will discuss our system architecture of our design. So our system is mainly divided into three main parts, which is the input unit, the processing unit, and lastly the output unit. So if we see the block diagram, we will understand the thing better. So here this 3 into 4 matrix keypad is being used as our input unit. The 89C51 51 microcontroller is as using as our uh, processing unit, and lastly the 16 into 2 LCD display is using as our output unit, and there are pins connected to respective ports, and there are reset circuit. Oscillator is being used, 5-volt power supply is given. So if we see the protest circuit, we'll understand it much better and understand it clearer. So in the input unit, we are using chain to 4 matrix keypad. The rows are connected to port 3 and columns are connected to port 2. And our microcontroller will scans the rows and columns, and this is how it will detect which key is being pressed. So this design is actually making the whole thing efficient, as will only require 7 input output pins here. If we use individual button, so we would have needing 9 input output pins. So nine, but here we are only needing 7 input output pins. Uh, then in the processing unit, it will reach the keypad input, executes the game logic, stores game state in RAM, and also it will control the LCD, and it will use the 12 megahertz crystal oscillator for clock pulse, a research circuit for proper startup. Uh, in the output unit, it will use a 16 into we will use a 16 into 2 LCD display. It will provide us a clear visual feedback with plus text. The data lines are connected to port 1. For the control signals, RS is connected to pin 0.0, RW is connected to 0.1 pin, and enable pin is connected to pin 0.2. So if we talk about a bit about our working process, so the keypad will send the input to microcontroller in order to process it. So the 898C51 processes its input, then updates the game state stored in internal memory, and displays the updated board and display a message on the LCD. In the player versus AI mode, The microcontroller also generates moves using a rule-based AI algorithm, which will be elaborated later by my teammate. Now, my teammate will explain the hardware design in details.
Now I will explain the hardware design of our system. Our complete circuit was designed and simulated using Proteus, and it integrates all required components for a fully functional embedded gaming device. The hardware consists of several key components like AT89C5 microcontroller, 12 MHz crystal oscillator, reset circuit, a 3 into 4 matrix keypad, a 16 into 2 LCD display, and a pull-up register network. Each of the components plays a significant role in ensuring stable and efficient system operation. At the core of our hardware, we have AT89C51 microcontroller, which acts as the central processing unit. All input, processing, and output operations are controlled through this microcontroller. We use a 12 MHz crystal oscillator connected to the XTAL1 and XTAL2 pins of the microcontroller. This provides a stable clock signal required for the instruction execution and proper timing operations. Now the reset circuit. It consists of a 10 kilo ohm resistor and a capacitor, which ensures that if the microcontroller starts from a known state whenever the system is powered on, this prevents unpredictable behavior during the startup. For our user interface, we use a 3 into 4 matrix keypad. The rows are connected to the port 3 and the columns are connected to the port 2. A pull-up resistor network is used to the port 2 to ensure the stable and noise-free input signals. The matrix configurations allows us only 7 input output pin uses, which is very efficient given the limited pin availability of the 8051 microcontroller. The microcontroller scans the rows and columns to detect which key is pressed. For our output, we are using a 16 into 2 LCD module. The LCD interface is in 8-bit mode for the faster and simpler communication. Data lines are connected to the port 1 and the control signals are connected to the port 0. Here, RS is connected to the port 0.0, RW is the connected to the port 0.1, and EN is the connected to the port 0.2. This configuration allows the controller to send both commands and data efficiently to the display. The LCD monitor provides a clear visual feedback, including the gaming board, player turns, and the game results. The overall interfacing is designed to optimize input output uses and to maintain simplicity. Port 1 is designed for the LCD data, port 0 is for the LCD control signal, and port 2 and 3 are used for the keypad interface. This separation ensures that the input output operation don't interfere with each other. These hardware designs offer several advantages like efficient use of limited input-output units, low cost and easily available components, stable and reliable operation, and simple and modular design. Most importantly, it meets all the project constraints including low power consumption, low cost, and limited hardware resource. In summary, our hardware design successfully integrated all the components in a compact and efficient system, providing a foundation for the software and the game logic implementation. Now I will pass it to my teammate for the software and game logic explanation.
Here in my presentation, I will explain about the software part along with the code. We have implemented the circuit in Proteus. My teammate has already described about the architecture of the design and the components that have used by us in this circuit. Now I will dive into the explanation of the circuit and how it runs. When I start the Proteus file, it will show two options in the LCD display. One is player versus player, and another is player versus AI. If I want to play player versus player, I have to select one here, which can be done by the keyboard interfacing, which is shown here. As it is a 3 by 3 matrix, it will start count from 1 to 10, 1 to 9. As you can see, there is the top leftmost position, which is considered as 1, and then row wise it will go like 2, 3, 4, 5, 6, 7, 8, 9. I have started counting from 0 in the code, in the assembly code, and that has ended to 8. Now, for the ease of my description, I have started from 1 to 9 in this Proteus code description. Now, if I press 1 in the display, it will show this kind of interface where it is telling that player 1. I have programmed this like it will always start from player 1. When the player 1 presses the input from the LCD, here it will exactly in the same position as I have pressed the button. Like here for the player 2, if I press here, it will show in the center position, which is 5. Now, if I uh, place my player X input in the position 9, it will show in the exactly same position. Now, here, as an example, I will make a blunder being the player 2, and the display shows that the player 1 wins. How is it done? There is a lookup table for winning where there is 8 different combination of winning. I can show this from the code. Here there is 0 to 8 number, what I have said earlier. In my code, there is a first winning combination of 0, 1, 2, which is this 0, 1, 2. Then 3, 5, 3, 4, 5, 6, 7, 8. It's all are row wise. Then 0, 3, 6, 1, 4, 7, 2, 5, 8. It is column wise. Then if we can win by diagonally. So there is a combination like 0, 4, 8 and 2, 4, 6, which is this 0, 4, 8, 2, 4, 6. Whenever it matches with the input of mine, it shows that the specific player have won the game. I can give an example where player 2 wins. So there can be a question that how my code knows when there is a draw. If I use this code like there is a draw, now how does my code knows that there is a draw? When my LCD gets exactly 9 inputs and none of the combination matches from the winning table, it gives a draw as an output. As you can see, whether there is the end of the game, the LCD restores and give us these two choices again. Now, if I choose player versus AI now, here I have programmed like every time I will start the game as player 1. Here my AI works like in 5 steps. Its first priority is to get a winning combination, which is shown here. If I am getting the winning combination, it will block my way, which is its second priority. The third is it will always want to capture the center position first, this one, the center position, and if it is captured, it will go for the corners, which is 1, 3, 7, 9. And if these are also captured, it will go for the edges like 2, 4, 6, 8 number position respectively. If you see the game of an AI, you will see the pattern as I said. When I am giving here, the output is in the center position. Now, if I am giving here, it will giving a position in the corner. Now, here is a winning combination. Now, if I block it, it will go for the edges. Now, there is a classic way to win a game by taking X, which is when I start the play with the position X in the corner, and then if the AI as priorities takes the center, I can position my X in the other corner and the AI as well as will go for the second corner, as you see. Now, if I now block this way, there is no chance of losing unless I am dumb. I can play this like here. If I choose the corner position, it will always capture the center. Now, if I choose the another corner position, it will always choose the other corner. Now, if I give the input in the seventh position, the AI have taken the edge, which is eighth position. Now, as you see, it have taken this edge because it wants to block me here, but I am also winning in this position. So it is one of my limitations of this AI. I couldn't fix this for the shortage of time, but with Minimax algorithm, it can easily be fixed. I can also give you an example where AI wins. Here my AI has win. Here AI has won. So that's all for the description on how the Proteus file works. The code part will be attached to the Google Classroom file, and the algorithm of this code has already been described here. Thank you.
Now I will present the cost, power analysis and overall conclusion of our project. Our system is designed to be energy efficient where the microcontroller consumes around 15 mA and the LCD display consumes about 2 mA, making the total power consumption approximately 18 mA. If we consider 8 hours of continuous gameplay, the required capacity is around 144 mAh. By using a standard 2AA batteries, the system can run for more than 100 hours, which makes it highly suitable for portable use. One of the main goals of our project was affordability, and the total prototype cost is around 500 BDT, where the main cost components include the microcontroller and the LCD display. Despite this low cost, the system delivers reliable performance and a complete gaming experience. The key advantages of our system are that it is low cost, portable, lightweight, energy efficient, simple to use, and does not require any internet or external devices. In conclusion, we have successfully developed a retro-styled handheld tic-tac-toe gaming device using the AT89C51 microcontroller. This project demonstrates how a simple embedded system can deliver an interactive gaming experience even with limited memory and hardware resources, while also highlighting important concepts like embedded system design, hardware-software integration, and efficient programming under constraints. In the future, the system can be improved by adding sound effects, enhancing the AI with more advanced algorithms, using a graphical display instead of an LCD, and expanding the system to support multiple games. Thank you.